Good afternoon, everybody. Welcome. It's good to see you. So today we're going to study a arcane area of computer systems known as floating point, which is the way that computer systems represent the real numbers. So you're all familiar with decimals, something like 3.14. And there's a similar idea with binary numbers. Okay, so what does a fractional binary number like 1011.101 represent, and how does that work? Well, it works just like the fractional decimal numbers that you're used to. So you have in this case, it's a binary point, and to the left of the binary point, you have bit positions representing powers of 2. So 2 to the 0, 2 to the 1, 2 to the 2. So 1/2. 1, 2, 4, and so on. And to the right of the binary point, you have 2 to the -1, 1/2, 2 to the -2, 1/4, 2 to the -3, 1/8, and so on. And so we can represent any fractional binary number using this notation, where we sum the bit at position k times 2 to the k. Okay, so it really works exactly the same way as with base 10, just with base 2. So let's look at some of these values. So 5 3/4 we would represent as 101.11. So this is before plus 1 is 5, plus 1/2 plus 1/4. Okay, so 2/4 plus 1/4 is 3/4, so 5 3/4. Okay, so that's pretty simple. 2 7/8 is 10.111. So that 10 is 2, of course. And then 0.111 is 1/2. So 4/8 plus 1/4 is 2/8 plus 1/8. Okay, so 7/8. And 1 7/16 would be 1.0111. So that the 1 to the left of the binary point is 1. And then we have 1/4 plus 1/8 plus 1/16. So 1/4 is 4/16. 1/8 is 2/16, and 1/16. So you add those up, you get 7/16. Okay, now notice for some of these numbers, this bit pattern 101.11, if we shift it to the right to get 10.111, we've divided by 2, right? So we've taken 5 3/4 and divided it by 2. And it works the other way too. If you shift to the left, you multiply. If you shift to the left by 1, you multiply by 1. And these numbers that are all 1s to the right of the binary point these are numbers that are just slightly less than 1. Okay. And so when we want to represent those, we'll often we'll sometimes refer to those numbers of that form as 1 minus epsilon, and epsilon just depends on how many bits you have to the right of the binary point. So epsilon gets smaller the more of those bits you have, or it gets closer to 1, and epsilon gets smaller the more of those bits you have. Now there's limitations in this kind of representation. So first of all, we can only represent rational numbers of the form x divided by 2 to the k. We can only represent numbers of that form exactly. Other numbers have to get have repeating bit representations that can't be represented with a finite number of bits that we have in a computer system. So for example, things like 1/3 is this repeating representation, 1/5 and 1/10 are other examples of that. Now the other problem we have is that we can only there's only so many bits to the left and the right of the binary point. So we're kind of if we move the binary point to the left, then we don't have as many, we can't represent as many large numbers. We can only represent small numbers, but we have more precision to the right of the binary point. Right? So we can represent more fractional values. Just the range of those values will be much smaller. Similarly, if we move the binary point to the right, we'll have a larger range of values, but we won't be able to represent as many fractions. Okay. So there's this kind of trade-off, and floating point is a representation that enables us to move that, basically to move that binary point to represent sort of as wide a range as possible with as much precision, given the number of bits, the finite number of bits that we have to work with. So the float and floating point is this sort of shifting binary point, right? This floating binary point. Now, up until 1985, floating point was just a disaster. And every computer manufacturer had their own representation. You couldn't, and it was just terrible because you couldn't predict what would happen if you moved your program from one machine to another. The behavior would be different, the rounding would be different. It was a very difficult situation, and people really, computer scientists in particular, really disliked floating point. In 1985, IEEE, which is the Professional Association for Electrical Engineers, introduced and it's also a very important standards body. They introduced a standard floating point representation called IEEE floating point, which was then adopted by all computer manufacturers. So now the situation's much better. Everybody supports the same kind of floating point representation, which is what we're going to learn about today. So the floating point has the form, it represents numbers in this is like a scientific notation. It represents numbers of the form -1 to the s, where s is a sign bit, times a significant m, okay, times 2 to some exponent e. Okay, so all of the numbers that we can represent in floating point have to be represented in this form. So the sign bit s determines whether the number is negative or positive, obviously. The significant m, so this is sometimes called a mantissa, which is where the m comes from. The significant m normally is a fractional value in the range between 1 and 2. And we'll see why that is in a second. And then the exponent e weights the value by some power of 2. Okay, so this is encoded in either 32 bits or 64 bits in the following way. The sign bit s is the most significant bit. And then this is followed by some number of by some number of bits called the exp field, which encodes the exponent e, but it's not identical to e. It encodes e, and we'll see how that works. And then and then that's followed. The remaining bits are the frac field, which encodes m but isn't identical to m. Now IEEE floating point provides two different kinds of floating point. There's single precision, 32 bits, and so-called double precision, which is 64 bits. There's this funky Intel extended precision, which is non-standard, and we won't talk about it anymore. And so in the single precision, 32 bits, you have one signed bit. There's always a signed bit. You have 8 EXP bits, and you have 23 frac bits. In double precision, you have 11 EXP bits and 52 frac bits. Now, there's a number of different kinds of floating point representations. The sort of the default and sort of the common representation is called normalized, so-called normalized values. And normalized values are all the values where the EXP field is not equal to 0 and not equal to all zeros and not equal to all ones. Okay, so everything, all zeros and all ones are special kinds of numbers we'll look at in a second. So the exponent, this exponent e, remember our numbers are minus 1 to the power s times m times 2 raised to the power e. The exponent e is encoded as this biased value, which is called exp. So the exponent e is exp minus some bias. And exp is the value, capital exp is the value of the exp bits, the bits in the exp field, treated as a positive number. Okay, so capital exp is just, you just look at it as an unsigned 7-bit, in the case of single precision, 7-bit number. Okay, now the bias is 2 to the power k minus 1, where k is the number of exponent bits. Okay, so for single precision, we have 8 exponent bits. So 2 to the 8th, 2 to the 8 minus 1 is 7. So 2 to the 7th is 128. Minus 1 is 127. Okay, so the bias for single precision is 127. And similarly for double precision, it's 1023. Okay, so you just have to memorize this formula. The exponent e is the exp field interpreted as an unsigned number minus the bias. Now this is kind of a strange thing. The first time you encounter floating point, it seems kind of odd, right? So why not? I mean, we've already learned about 2's complement. That's a perfectly fine way to represent positive and negative numbers, right? And we have exponents that are negative and positive, right? So why not just use the exp field to represent, or why not just use 2's complement in the exp field to represent those positive and negative exponents, right? So it turns out that the reason that they do this is that, and if you think about this, and we'll come back to it, but if we encode the exponent e using this bias representation, the smallest negative exponent is represented by all zeros. Okay, and the largest exponent is represented by 0, 1, 1, 1, 1. Okay. So the number with the smallest exponent, if we were just to compare the bits using just some kind of unsigned representation, just comparing the bits, treating it as an unsigned number, by using this biased representation, we can just compare 2 floating point numbers just as unsigned. We can treat the whole floating point number as an unsigned integer and compare 2 numbers and get a true comparison. Okay. So the exponent uses this sort of biasing encoding, and then the significand is encoded with an implied 1. So and this is where the normalized, in the normalized representation comes from. That we're always going to represent our numbers. So m, we're always going to normalize m, no matter what the number we want to represent. We're always going to normalize m as 1 point something. And then we adjust the exponent accordingly. Right? So if the value we want to represent is 100.01, we're going to shift it over, and it'll be 1.00. Okay. And then we'll adjust the exponent to represent that shift. Okay, so the bits in the frac field, xxxxx, are all of the numbers to the right of the binary point. Right? So there's always this implied 1. But we don't even encode it. We just throw it away because it's always there. Right? So this is a little trick just to get one more bit for free. Okay, so the XXX bits in the frac field are all the bits to the right of the binary point after 1 point, the 1 point. And this is the smallest frac field is all zeros, which corresponds to a significand of 1.0. Okay. And a frac field of all ones corresponds to 2 minus epsilon. So that's 1.11111, and so on. So let's look at an example. So let's look at how we would encode 15213, which is our favorite number, in floating point. So if we represent that, so it's an integer, and we represent it using these bits, take my word for it, correspond to the integer 213. So now we want to convert it, we want to normalize it by expressing it as 1.110 and so on times 2 to the 13th. Okay, same number, we just normalized it so that there's always this leading 1. So the significand m is 1.11011 and so on. The frac field is everything to the right of the binary point. So we throw this 1 away, and we just take the values to the right of the binary point, and then we pad it out with zeros to get the 23 bits that we need for single precision. Okay, so now we've got our frac field. The exponent, so in this case, right, e is, we're multiplying by 2 to the 13th. So e is 13. So we want to represent the value 13 using this biased encoding. So the bias is 127. And so the exponent, the value of the EXP field should be 140. Because if we take 140 minus 127, we get 13. Okay, so 140 is represented using these 8 bits, and that becomes our EXP field. Okay, so the resulting floating point number, and of course it's a positive number, so the sign bit is 0. So the resulting floating point number has the 8 bits in the EXP field that we computed by subtracting 127 from 140, and then the frac field are these bits that we got here by just taking everything to the right of the binary point. So let's look at this exponent just a little bit more, because I think it can be a little confusing. So in our example, if we want to look at the range of EXP, So what's the smallest value of EXP? What's the smallest value of EXP? Now wait a minute, don't confuse the encoding with the value it represents. EXP is just the encoding. So what's the smallest value of EXP? 0, that's right. Okay, and the largest value is what? Remember? What's the largest value? Yes? Well, the largest value would be, remember it can't be all ones. Right? So the largest value would be 2 to the 8th minus 1. So, okay, so the largest value would be 0, 1, 1, 1, 1, 0 followed by 7 ones. Okay. So that's 2 to the 8th minus 1 is 255. Good. Okay, so then what's the range then of E, which is the actual value that we want to encode? Okay, remember, use this. We have this definition. So we have the range of values for EXP. We have our bias. So what is the range of values for E? This is the actual exponents that we're encoding. So what's the smallest exponent? Minus 127, good. Right, because that's 0 is our smallest EXP minus the bias, which is 127. Okay, so the smallest value of E is 127, and the largest value of E is so if we take the largest value of EXP, that's 255 minus 127, 128. Okay, so the numbers that we can represent using this bias notation will have the smallest exponent will be 2 to the minus 127, and the largest exponent will be 2 to the raised to the power 128. Okay, so do you see what's going on here? So we have a range of values for E. Here's the largest value, here's the smallest value, here's 0 right in the middle. These are the values we want to represent. This biasing is like a shift. Now we're shifting up by 127 so that now the smallest exponent is represented by 0. Okay. Any questions about that? Now, these normalized values always have this implied 1, okay, which when we want to represent numbers closer to 0, that limits us, right? So there's another type of floating point number called a denormalized value, which is characterized by an EXP field of all zeros. And in a denormalized number, or denorm, there's no implied 1. Okay, so the significant M is represented exactly, is encoded identically in the frac field. So there's no implied 1, and all of the numbers are the form 0 point something, something, something after them. And the exponent value E, instead of, you remember for denorms we subtracted bias from EXP. For denorms we subtract the bias from 1. Okay. Now if we just use the definition we use for normalized numbers, that would be the EXP would be 0. So we don't do that. Instead E is 1 minus the bias. And then the significand is coded with an implied leading 0 instead of a leading 1, like I mentioned. So So when exp is 0, and also, I mean, think about it. If we only had denormalized numbers, we wouldn't be able to represent 0, right? Because there'd always be a 1 in there. So for denorms allow us to represent 0, and they allow us to represent values that are very close to 0. So when the exponent is 0, and the exp field is 0, and the frac field is 0, then this is the 0 value. And so this is nice because all zeros represents 0, which is sort of what you want. Now there is this sort of weird thing, though, that if you have the sign bit is 1, and then your frac and exp are 0, then you have negative 0. So you have this kind of odd situation where there's a positive and negative 0. Okay. And other values, if exp is 0 and you have a non-zero frac, then those are the equally spaced numbers that are closest to 0. Now there's a couple of other special values. When exp is all 1s and the frac is all 0s, this represents the value infinity. So this is a value that we get when we do some kind of addition or multiplication and we overflow. So in floating point always overflows to this special value called infinity, either positive or negative infinity. So it's different from 2's complement, right, where you sort of overflowed in this modular way back around into the range of numbers. In floating point, we just overflow to this sticky value called infinity, and then everything we do on that remains infinity. So for example, if we did if we did 1 divided by 0, or minus 1 divided by minus 0, we'd get positive infinity. If we divide 1 by 0, negative 0, we get negative infinity. The fourth kind of special case, special number, is the case where the exponent again is all 1s, but the frac is non-zero, any non-zero value. And this represents what's called not a number. So this handles cases where there's no answer. There's no feasible answer. For example, if we try to take the square root of minus 1, what we'll get back is not a number. Okay. So I think it's helpful to visualize the number line now. So we have positive 0, negative 0, sort of right next to each other, and then to the right of that are the positive denorms, and then those sort of transition into the normalized numbers, and then you have infinity, positive infinity. You have a similar situation for the negative numbers, and then negative and positive not a numbers. So I think you've probably discovered now that a really good way to try to understand these numeric encodings is just to do examples with only a few number of bits. If you want to understand, like for example in 2's complement, if you want to understand Tmin and Tmax and how they relate to each other, just do a 3-bit 2's complement system. Imagine you just have a system with 2's complement, 3 bits, and then you can just enumerate all the possibilities, and you can see, and then you see where, the Tmin is actually 1 greater than Tmax. So if you add 1 to Tmax, it actually overflows into Tmin. Similar thing for floating point. I would really encourage you to do this. Just try some simple examples with a small number of exp and frac bits. So in this case, we're going to look at a floating point system based on IEEE that has 4 exp bits and 3 frac bits. As always, the sign bit is the most significant bit, followed by exp, followed by frac. Okay, so this is identical to IEEE floating point except for the size of EXP and frac fields. So it's actually small enough that we can now just enumerate these values. And, and now you can start to see why these weird definitions for the exponent in d-norms and normalized numbers. So let's just look at, so what we've done here, we've just, with a sign bit of 0, we've just enumerated all of the 2 to the 7th possible combinations of EXP and frac fields, starting with 0. Okay, so when EXP is all zeros, that's a d-norm, right, by definition. And then we have the 3 frac bits are all 0. Okay, so remember the EXP is all zeros, right? So for d-norms, the exponent value is 1 minus the bias. Our bias here is 7. Okay, so 1 minus 7 gives us a value for the exponent of minus 6. So we're going to take the frac, the bits in the frac field, times, so m is 0. So m in this case is 0 times 2 to the minus 6th gives us 0. Okay, so this is our representation of 0. And like I said, it's nice that it actually is, if we just treated this as an unsigned integer, it would be 0. Okay, so that's kind of pleasing. Now let's look at the very next number, right? The EXP is still 0, and we've just bumped up frac by 1. Okay, so again, it's 1 minus the bias, which is minus 6. And now this frac field represents, this is 1/2, 1/4, 1/8. So it represents, so this is a value of m is 1/8. So 1/8 times 2 to the minus 6, which is 1/64, equals 1 over 512. So in this floating point system, the smallest non-zero number we can represent is the denormalized representation of 1 over 512. The next smallest number is 0. Right? Okay, now let's look at, so let's bump this up by 1. So now we get a frac field of 0, 1, 0. So this represents 1/4. So em is 1/4. The significand is 1/4 times 2 to the minus 6. So 2/8 times 1/64 is 2 to the 5/12. Okay, so the numbers were just, by incrementing this, by incrementing our significand, we're increasing the numbers by 1 over 512. Now the largest d-norm in this number system is the case where the frac field is all 1s. And so this encodes 1/2 plus 1/4 plus 1/8, which is 7/8. And then our value is 7/8 times 2 to the minus 6, or 1 over 64, and that equals 7 5/12. So this 7 over 5/12 is the largest denormalized number we can represent in this system. And now if we bump our number up by 1, the frac field resets to 0, and now the EXP field goes from 0 to 1. Now, because the EXP field is non-zero, this is no longer a denormalized number, it's a normalized number. Okay, so now we're changing the definition of E from 1 minus the bias to EXP minus the bias. So what's EXP in this case? 1. Minus 7, the bias, is minus 6. So lo and behold, it's the same exponent as the previous denormalized number. So this is actually very clever by the IEEE folks. because you get this nice smooth transition from denorms to norms, to normalized. So you can see that our exponent e is minus 6 still. And now our, because we're taking 1 minus the bias 7, and our significand, now remember this is a normalized number because the exp field is non-zero. A Frac field of all zeros represents a significand of 1.000. Okay, so this normalized number, the smallest normalized number, is 1.000, which is 8/8, times 2 to the minus 6, which is 1 over 64, which gives us 8 over 512. So we've made this nice smooth transition from 7 over 512 to 8 over 512. And I'll do one more. I don't want to. So if we bump keeping the exp field at 1, if we bump our Frac field from 0 to 1, now this represents the significand of 1.001, which is 8/8 plus 1/8. Okay. So that's 9/8 times, and then the value is 9/8 times 2 to the minus 6, 1 over 64, which is equal to 9 over 512. Okay? Any questions about that? Question back here?
Yeah. How do you choose the bias? Like, why do you put the bias to start with k-1?
Okay, the question is why do you choose the bias to be 2 to the k minus 1 minus 1? Well, go back to my finger diagram here. So this is the range of exp fields that you want to, this is the range of E that you want to represent with 0 in the middle. Okay. And so you want to bias it so that this is halfway. 0, the smallest exponent is halfway to 0. So you want the bias to shift it up so that the smallest value of exp corresponds to the smallest exponent. Right? So 2 to the k minus 1 minus 1 is just giving you a value that's halfway between the smallest exponent and the largest exponent. Okay. That's good. Any other questions? Okay, if we take a smaller 6-bit format, same thing as we did before, just different numbers of bits in exp and frac, and then we plot these on the number line, you can see that the values are very dense around 0, so they're very spaced very closely together. And then every time you increase the exponent by 1, the numbers are spaced twice as far apart as the numbers that were represented by the previous exponent. So you can see, like in this little example, you see these values here are all equally spaced. These 4 values are equally spaced, and they're right next to each other. And then you see this jump in the spacing. That represents an increase in the exp field by 1. And then that spacing doubles as we go out. And you can see it even better here. If we zoom in, these blue values are denorms, and then we have the next set of normalized values where the Frac field is 1. They're spaced the same, right? We saw this when we kept increasing by 1 over 512. And then we increase the exponent by 1, and the spacing doubles. Okay, so this, like I mentioned, this encoding has some pretty nice properties. the floating point 0 is encoded as integer 0, which is nice. And with the exception of not a number, you can compare any floating point numbers, including infinity, by just treating it as doing an unsigned comparison. So that's really nice too. Now, when you add and multiply floating point numbers, right, we're dealing with a limited set of bits here. So if we take two numbers encoded as floating point and we add them together, there's no guarantee that we'll be able to fit all those bits in the bits we have available to us. There's no guarantee that we'll be able to fit the bits in the result. So what we do in this case is, you can imagine the model you want to have of floating point operations, addition and multiplication, is that you add or multiply, you do the addition or multiplication, and you compute the exact result. You just assume that you have an infinite number of bits. And then you use a technique called rounding to get it to fit into the available bits. Okay, so the effect is, like if doing, say, x plus y is getting the precise value of x plus y at an infinite number of bits and then rounding into the available bits. So let's look at this idea of rounding. This can be confusing the first time you see it. It requires, you need to think about it carefully to get it right. Now in IEEE there's 4 different kinds of rounding. There's round towards 0, round down, round to minus infinity, round up to, which is rounding it to positive infinity, and then the default case, which is the only one we're really going to consider, which is round to the nearest even. And this is what IEEE does by default. You can, if you go into assembly language, you can change that rounding, but we're not going to consider it anymore. Yes, question?
Negative infinity apart from the positive infinity?
I'm sorry?
Is there a distinct negative infinity apart from positive?
There is, right? Because there's one. So the question is there a distinct negative infinity and a distinct positive infinity? And there is. They have the exact same bit representation, except the most significant bit for negative infinity is 1. And for positive infinity, it's 0. Okay. Yes, question?
Why does nearest even round to 1 for 140?
Why does nearest even?
Round to 1 for 140.
Oh, I'll show you. Let me go over the others. The question was about nearest even. Yes?
Doesn't that make negative infinity greater than positive?
Well, that was the exception, right? That's right. So aside from infinity, you can't do that comparison.
But how about
Positive infinity works, right? But not negative. So you're right. Good point. All right, so let's look at these rounding modes, and I'll explain why the nearest even works. But let's look at, so rounding towards 0, what we're going to do, we'll use dollars. So we want to round to the nearest dollar. Towards 0, just anything less than, you just round towards 0. So $1.40 would go to 1, $1.60 would go down to 1, $1.50 to 1, $2.50 would go to 2, negative 150, you round towards 0, so that would be negative 1. Round down towards negative infinity, it's similar. The only difference is that for negative $1.50, you'd round towards negative infinity, which would be minus 2. Rounding up is symmetric to round down. The interesting case is round to nearest even. Interesting because it's what IEEE floating point actually uses. So the idea here, if you have a value that's less than half, then you round down. If you have a value that's more than halfway between two dollar amounts, you round up. The nearest even part comes when you have something that's exactly halfway. Then what you do is you round towards the nearest even number. Okay. So in this example, $1.40, because it's less than half, rounds down to $1. $1.60 is greater than half, so we round up to $2. $1.50, right in the middle, we round up to the nearest even dollar amount, which is $2. $2.50, we round down to the nearest even, right? If we round it up, it would be 3, which is an odd number. And minus $1.50, we round to we round down to minus $2. So the reason we do this, the reason they chose this, is that statistically, if you would imagine, if you have a uniform distribution of sort of numbers, they're going to round up or down about 50% of the time. So there won't be a statistical bias rounding up or down one way or the other. Okay, so that's the reason they did that. Now, you can apply this. You can do this rounding to any value. So in the last example, we did it to the nearest dollar. But suppose we wanted to round to the nearest hundredth using round to even, the default round to even mode. So we want to round to the nearest hundredth is this second position. This first we have tenths, then hundredths. So if we have a value 7.894999, that's less than halfway, right? Halfway would be any number that had a 5 followed by all zeros. So 4999 is less than that. So we would just round down to 7.89, even though 9 is odd. The only time we're going to apply round to even is when we're exactly halfway. Okay, the next example, 7.895001, that's greater than halfway, right? If this was a 0, it would be exactly halfway. So we round up to 7.9. Okay, now here's the interesting case where we have 7.895 followed by all zeros. That's exactly halfway. So now we apply the round to nearest even rule. 9 is an odd number, so that doesn't work. So we round up, and we do that basically by adding a 5 here. So 5 and 5 is 10, and then that carries over to the next position, and 9 and 1 is 0. 9 and 1 is 10, so that carries over, and so 8 plus 1 is 9. So the result of rounding up is 7.90. Okay, is that clear? Do you see? It's a very mechanical way. When you round up, it's a very mechanical like that. You always just add the halfway number, in this case 5, and then just propagate it out. Just do the addition, and that'll give you the nearest. That'll round you up to the nearest hundredth in this case. Okay, now the last case, 7.885 followed by all zeros, that's another number that's halfway between two numbers rounded to the nearest hundredth. So in this case, 8 is even, so we round down, and to round down we just truncate. Just throw these bits, these digits away, and we get 7.88. So are there any questions about this? Question back here, yes?
I have a question kind of going back up in slide, not exactly this. But so is it true that everything of the same exponent, or that has the same x field, will be equivalently spaced? Is that how it works?
Yes, so the question was if numbers that have the same EXP field, will those numbers be equally spaced on the number line? And the answer is yes. Yes, question?
Yes, so I want to ask if when we're rounding up or down, we consider all the entire value to the right of the place we're rounding. Like if in the last example there was a 1 at the end, it would round up.
It would round up. yeah, the only, the halfway values are always, in this case, because it's base 10, the halfway number in base 10 is 5. And then, so it's always the halfway number, in this case 5, followed by all zeros. You'll always have that, the halfway, if a value is halfway between like 200ths, it'll always have that form. All right, now we can do the same thing with binary fractional numbers as well. Now, a binary number is even if the least significant digit is 0. Okay, we only have 2 digits, right? So odd is 1 and 0 is even. Okay, and the halfway, so the halfway value is going to be a 1 followed by all zeros. Okay, that represents exactly halfway. Okay, so it's analogous to the base 10 example, except where the halfway value is going to be 1 followed by all zeros. So let's look at some examples. So suppose we want to represent 2 and 3 30-seconds. And suppose we only have 4 bits to do that in. Okay, well, to represent that exactly, we need 7 bits. And so we have to round. Okay. So let's look at, so we're going to round to this 2 bits right of the binary point. And so let's look at all the bits that follow that. So since it starts with 0, this is going to be less than halfway. So since it's less than halfway, we just truncate, just chop those out, and the result is 10.00. Now our next example is 10.00110. So if we look at these, the bits to the right of the bit we're rounding to, since it starts with 1 and it's not followed by all zeros, that's greater than half. Okay. So in this case, we have to round up. And so the way we do that is we take 1 and we add it to this leftmost 1 right here and just do the addition, and the result is 10.01. Now let's look at 2 to the 7/8. This is represented as 10.11100. Now here's that halfway marker that we were looking for. It's a 1 followed by all zeros. So this is exactly halfway. So now we have to round to the nearest even number. Now, if we can't just truncate, because then that would be an odd number, right? It would end 0.11 is an odd number. So we have to round up, and we do that by adding a 1 right here to this leftmost red bit. We add 1 to that, and then just do the addition, and we end up with 11.00, which is 3. So the nearest value to 2 to the 7/8, the nearest rounded value is 3. Okay, our last example, 2 to the 5/8, we have the same halfway marker again, 100. But in this case, the 100th bit, or the 1/4 bit, is 0, so that's even. So we can just truncate. We just throw those bits away, and the result is simply 10.10. That makes sense? So it's very mechanical. Mainly, you just need to be able to recognize that halfway marker, and then figure out if you need to round up or down. If you're going to round down, just truncate. If you're going to round up, add a 1 and just propagate it to get your result. Okay. Now we won't spend much time. I just want to mention a few things about multiplication and addition. So if we multiply 2 numbers, so we have different mantisses, significants, and exponents, And suppose that the result is m times 2 to the e. The sign bit will be the XOR of the two sign bits of the two operands. The significant m will be the multiplying m1 times m2, and the exponents are added, right? Because just by the rules of exponents. So if m is greater than 2, and this is a normalized number, we have to shift it. We have to put it in the range between 1 and 2 by shifting to the right and incrementing the exponent. If e is out of range, then we overflow to infinity. And then if m has too many bits, we have to use round to even to fit it into the available frac bits. Okay, addition. So suppose we're trying to add two floating point numbers. Conceptually, what you do is think of those numbers as fractional binary numbers. You want to line up the binary points, then do the addition, and then do the addition, and then normalize the number so that normalize the significance so that it's between 1 and 2. And you either do that by shifting right or left. If e is too big, then you overflow, and then you round the bits in m to fit into the available frac field. Now you remember when the first day of class, we talked about what we call these great realities, that ints aren't really integers and floats aren't really reals. So just as we saw when we looked at 2's complement representation of integers, they're not exactly like real integers, and operations on them aren't exactly like real integers, but they follow very predictable mathematical properties, okay, that are similar to integers, but not quite. So the same thing holds for floating point numbers. They follow very predictable, they have very predictable mathematical properties, but they're somewhat different from the reals. And the big thing is that the big thing with addition is that it doesn't associate. Okay, it's commutative, but it's not associative. And this usually happens when you're dealing with numbers that have very large dynamic ranges. So if you're trying to add and subtract really big numbers with really little numbers, you run into this problem of non-associativity. So the example was if we take 3.14 plus 2 to the 10th, 2 to the 10th is so much larger than 3.14 that when the bits that, it would be 2 to the 10th plus 3 to the 0.14, the bits that represent the 3.14, there's bits way out here that represent, there's one bit out here that represents 2 to the 10th, and then there's a few bits here that represent 3.14, and there's just not enough, we don't have enough bits to represent all those, so the 3.14 goes away. So adding a big number to a little number essentially gives the big number, and then if you subtract that big number, you get 0. Now, if we change the association, if we take this big number and subtract it from itself, we get 0, and then so the result will be, instead of 0 as before, we get 3.14. So other than that, you have all of the things that you would normally expect. Closed under addition, it's commutative, there's an additive identity of 0. Except for infinities and nans, there's an additive inverse. Right? You can take, for any number, there's an inverse that'll give you 0 when you add it together. And you get monotonicity between values, except, of course, for infinities and nans. Now, multiplication has, it's similar. It's closed generally under multiplication. It's commutative, but it's not associative, and it doesn't distribute over addition. And it's the same. So here you can see we're taking 2 to the 20th times 2 to the 20th times 2 to the 20th, and so that gives infinity. But if we reassociate and we take, 2 to the 20 times 2 to the 20th times 2 to the minus 20th. Well, this first multiplication is infinity, and anything you do with infinity is just infinity. So the result is infinity. However, if we reassociate and multiply 2 to the 20th times 2 to the minus 20th, that gives us 1, and then multiplied by 2 to the 20th, and so we get 2 to the 20th. So the big takeaway point here is that a floating point isn't associative. Okay. Now, is that a problem? It's something you have to be aware of. But generally, I mean, I've done a lot of scientific computing, in particular modeling earthquake ground motion in Southern California. So basically, we would build models of Southern California in the computer, and then we would shake them, and then we would see how the ground moves in like Los Angeles. Right? And that shaking, we used a numerical method called finite elements, and it used all floating point, single precision floating point numbers. And we never ran into a problem with this associativity, right? We would do operations in different orders. We couldn't always guarantee that we would do the operations in the exact same order. But we never ran into a problem with this because nature in general is kind of smooth, right? That if you look at if one part of the ground is shaking like this and you look at the next part, it might be shaking a little more or a little less, but you're not going to have like huge differences. And so we never ran into those kind of problems. But if you're simulating natural phenomena, you don't often see these kind of huge dynamic ranges. But other times, if it's not non-natural, maybe financial systems that use floating point, then you might see these larger dynamic ranges of numbers, and it might become a problem. So as a programmer, you just generally have to be aware of this. You have to have a sense for the dynamic range of your numbers, and you have to keep in mind that if you reassociate or change the order of things, you may not get exactly the same answer. Okay, now C gives us two different kinds of floating points. So the float is the IEEE single precision, and double is the IEEE double precision. Now, you remember when we did casting between ints and unsigned values back and forth, the cast never changed the bit representation. It just changed the way that, in fact, it never even changed how the ALU manipulated those bits. It's really just how we're interpreting and how we're viewing those values. However, when you do cast between floats and ints and doubles, the bit representation changes. Right? So a cast here has a dramatic effect on the actual bits themselves. Now, if we go from a double or a float to an int, it's going to truncate the fractional part and give us the integer part, and then round to fit. Oh, actually, no, there won't be. Okay, so think about this. How many there were? We said 23 frac bits in float, and I forget exactly how many in doubles. Anybody remember? Doesn't matter. It's some number. Well, no, it does matter. So for a float, if we cast a float to an int, we're casting 23, something that we can represent with 23, at most 23 frac bits into a 32-bit int. So we'll never lose. So we'll never need to do any rounding. But double precision has 52 bits. Okay, so there we might not be able to fit the represented integer into the int, so there'll have to be some rounding. Sorry, PowerPoint crashed. Okay. Right now, if we cast from an int to a double, we'll have enough bits so we won't lose anything, right? The 32 bits will fit in the double precision frac field. But int to float there's more bits in an int than there are in the frac field of a float, so we'll have to do some rounding, right? So casting works the same way as any other operation. You can think of it as just taking assume you have an infinite number of bits, get the exact result, and then round it to fit into the available bits. All right, so the final thing I want to do today is sort of test your understanding, solve some puzzles to test our understanding of these properties of floating point numbers. So imagine that we have three values: x is an int, f is a float, and d is a double. And then we're evaluating these C expressions. So is x equal to int float x? Yeah. Oh, you can edit out that other stuff? Okay. All right, so what do you think? If we take x, which is an int, cast it to a float, and then cast that back to an int, will that always be equal to x? No. Right, because we lose some bits, right? We don't have enough frac bits in float. What about if we take x, cast it to a double, and then cast it back to int? Will we always get equivalent value? Yeah, because we have enough frac bits in double. Now what if we take a float f, cast it to a double, and then cast it back to a float? Will that always equal the original f? Yeah. What about the converse, though? What if we take the double d, cast it to a float, and cast it back to a double? No. How about this? How about if we take f, negate it, and then negate that again? Will that always equal f? Yeah, because we're just toggling a bit, right? So okay, how about 2 over 3 equal 2 over 3.0? No, because 2 over 3 is 0. Okay. And 2 over 3.0 is a floating point value, 2/3. The floating point representation of 2/3. Okay, how about if the double d is less than 0? Does that imply that d times 2 is also less than 0? Yeah. Even if, no matter what, even if 2 times d overflows, it'll overflow to negative infinity, which is less than 0. Okay, how about, does the double d greater than f imply that minus f is greater than minus d? Yeah, that's that monotonicity right? And again, it's just, yes?
You said that 2 over 3.0 was a float. Is that a float or a double? Would that be a float or a double?
Oh, that's a good question. I think it'd be a float. I think if you put, there's an annotation in C to give it a double, but actually I'd have to check that out. That's
There's also one for floats, for F.
an F, yeah. That's a good question. I don't know. We'd have to check. I'll have to go and look in the C guide. How about if, is d squared, the double d squared, always greater than or equal to 0? Yes. And how about, does d plus f minus d always equal f? No, because of lack of associativity. Okay, so that was fun, right? Floating point's always fun. So anyway, the big thing is just to realize that floats aren't exactly really reals, but they have very, very predictable properties, and that they're not associative or commutative. They're not associative, and so you have to be careful about that. All right, well, have a good weekend, and we'll see you on Tuesday.